Hello everyone. I've had a lot of things going on since the last video I posted. Some of the stuff I videotaped, some of it I didn't. I'm going to talk to you a little bit about what I'm doing today. Recently I was doing a job on my vertical mill and I did something really stupid. The power went out. I was drilling a hole and I was almost to break through and the power went out. So I thought, cool, it's a good place to stop. I'll run and get some lunch and come back and hopefully the power will be back on. Well, I was gone just about an hour and I came back in, I flipped the lights on in the shop, they came on, I knew I had power, so I walked over to the mill, and as soon as I walked over to the mill, let me show you what I found out. Okay, right now this looks a little confusing because I've got the head upside down on the mill because I had to take the motor out, and it was easier to flip it upside down. I could take the bolts out and let the table or motor rest on the table, and I could take it out that way because that motor is very heavy. I'll show you in a minute. But when I got back, I realized I'd left the switch on, and as soon as I seen that, I knew I'd probably burnt the motor up in this mill. It's got a 3 horsepower, 3-phase induction motor on it, and I have a phase converter. That's what that green motor is on the floor, and that box up here, and it's got a magnetic switch on it. So when you hit the button, it starts up, but if the power fails, the switch disconnects. So when the power came back on, the inverter didn't kick on because the magnetic switch didn't engage, but because this is a mechanical switch, it was still engaged. And when you're running a 3-phase motor on single phase and you're using a phase converter, especially one with a magnetic switch and a rotary phase converter, it doesn't come on, but the power comes back to the switch, which basically it's sending 240 volt single phase into that motor. So the motor's sitting there humming and kind of fighting against itself trying to start, but because it doesn't have the third leg of power coming into it, it can't spin. So it just sits there and cooks. So I guess sitting there for an hour was too long. It burnt the whole stator up in it, and there's no quick fix to fix that. You either have to buy a new motor or you can get that motor rewound. This is the motor here that's out of the mill. And you can see it's just not a normal foot-mounted motor. It's what they call a C-face motor, because it mounts on the face of the end bell. It's got a flange here, and then the shaft is an odd length because this is a variable speed mill, so you can't just throw any motor in there. It's got to basically look like this on this end of the shaft. Now the issue is this motor, or this whole mill, I think was made in Taiwan, maybe. I'm not even sure where it was made. And there's no way I'm going to find an exact replacement for this motor. So the first thing I did is I called a couple of motor companies to see what they charged me to rewind it. They said around $1,200 to $1,500 to rewind this motor. I understand it's definitely worth that, but I'm not going to pay that for it when I know I can find just any C-face motor, and then I'll have to modify it, of course, which that's what I'm doing right now. I found this motor on eBay. It's a brand new motor, still in the box. And it's a 3-horse, 3-phase induction motor, so it's basically just like this motor as far as the power, but the dimensions on it are completely different. You can see the face on this one's completely different than this one. Again, it's no big deal. I've done this a million times in the past. I'll have to stub a piece of shafting on the end of this shaft and remachine it down to look like this shaft, to have the same dimension from this face to the end of the shaft when I get all done. Same as from here, from this face to the end of this shaft will have to be the same as this. So again, that's no big deal. I got this motor for, I had paid $290 for the motor on eBay, and then it was $100 shipping. It came from McChesney Park, Illinois, which is up by Rockford, Illinois, which is kind of weird. When I was 12 years old, this mini bike I have over here, and sorry, Lewis, I know I get distracted sometimes, I don't want to mention this. When I was 12 years old, my grandparents bought this mini bike for me, and I started riding it. We lived in the Marine Apartments, and the Marine Apartments are right behind, it's called McChesney Park now, but when I lived there when I was 12 years old, it was an airport, it was called McChesney Airport. And I rode this mini bike all over that airport. They had a lot of wooded area in the back and stuff. I mean, I didn't get up on the runways, but there was a lot of trails and stuff in the back of the property, rode all the time. After I moved away, it got bought out by some developer and they turned it into a shopping mall and changed the name to McChesney Park. So I thought it was kind of cool that This motor came from the same place basically where I used to ride my mini bike. So just a little bit of trivia. So what I have to do first, I'm going to take this apart and I'm going to machine this end bell down. I'm going to get rid of some of this material here, probably half of it down to this shoulder. I'm going to machine this off. And then I started cutting out over here a flange that I'll have to finish machining. I'll machine a step in it so it'll fit on that little step on the end bell and bolt in place, and then I'll put the 2 holes in it for mounting it on the mill. And I just finished cutting this out by hand with my plasma arc here, and I made a template. I made a template the actual size out of cardboard of what this flange needs to end up being. And then I made another template a 1/2 inch smaller on the outside to allow for the tip on my plasma to cut. So when I cut it out, it would be cutting it out the right size. And you can see after I cut it out, the diameter is pretty dang close. My ear's a little bit bigger, but these were a little bit small to begin with, and they're out in the open, so it won't hurt anything if they're a little bigger. I might even cut them down a little bit, I don't know. But I'm going to go ahead and cut out the inside now, and I'm just going to cut it out by hand, because when I put it in the lathe to cut that counter bore, I can go in there and bore this out. This diameter doesn't do anything. It's just clearance in there, so I could leave it rough cut out, but I'm going to clean it up just so it looks nice. So that's going to be my next step.
Okay, so now I'm setting up to weld this end onto the rotor shaft here so I can remachine it to the proper dimensions so that when I put it on the mill, the pulley and everything will line up. So what I had to do first, I had to cut the ends down, and you cut them down into a shape, kind of like a chisel point on it. And then the reason for that is, if you cut that a nice big radius, you're going to have an inch of weld to fill in here. So you can make it, kind of a chisel point, and then as you're welding, as you come back and forth, you can burn into each side, so you get 100% weld. It's very critical whenever you're stubbing a shaft that you get 100% penetration on this material with the welding rod. If you leave any kind of crack in there, in theory, it could eventually keep cracking and come out, and the shaft will break off. So that's really important. And of course, proper preparation, proper preheating, proper welding rod, proper post heating, and proper cool down is very critical to this working and holding up. Okay, so I just wanted to explain a little bit what I'm doing here. I've got a piece of angle iron to line these two pieces up together, so they're fairly close on the same center line, so they definitely will clean up. So this shaft diameter is an 1/8 inch smaller than this shaft diameter, so I have to shim it out a 1/16 on a side to offset the difference between the two. And then they should, when I put it together, they should line up with each other fairly closely. Now, when you start welding this, you got to weld one side, flip it over, weld the other side, keep working back and forth and check it, you know, spin it in some V-blocks and check and make sure that this is running close enough that it'll clean up when you machine it. It doesn't have to run perfect, just close enough so it'll clean up. And that was another reason why I left this an 1/8 inch bigger than this diameter, because this diameter has, I believe it's about 160 thousandths to come off of it to be the factory size for the variable speed pulley. So that leaves me even more out here, so that allows me more leeway out here for it to run out and still clean up. Now, if it was critical, I would weld up this keyway because it's not going to clean up 100%. It's still going to be in there a little bit. But I'm not going to worry about it on this particular application because it's not going to hurt anything. If I was doing this for a customer, I would weld that up so when I got the machine and cut the new keyway in it, you wouldn't see that anymore. And I'm also going to check and see if it's possible that I could cut my keyway back in here. The problem is, this is a standard 1/4 inch keyway. The keyway I got to put in there is metric, and I'm not sure what size it is, but dimensionally it's 234 thousandths wide, so it's about 16 thousandths narrower than this, so there's a chance part of it would not clean up. So I want a good keyway for my pulley, and it won't hurt anything if I put the keyway opposite this one and leave this one in there. So anyway, I'm going to go ahead and finish getting this all clamped together, and then we'll start welding it. Okay, we're all set up here in my V-blocks. I've got an angle iron clamp to the shaft, and I don't like using hose clamps because when you heat this shaft up, you got to heat it up to at least 900 degrees, and if you're not careful with your torch, you can melt through your hose clamps and the whole thing falls apart.
Normally I'll put big C-clamps or vice grips or something on this to hold it together, but I'm going to try to keep from getting too much heat in my hose clamp. So we'll see how this works out. Anyway, you can see I've got it clamped up where these two chisel points meet up here together. In theory, my first pass when I weld down through there, I should be able to burn through that crack to the other side. And then I'll take my slag hammer and knock the slag off, and then wire brush it, and I'll probably put maybe one more pass on this side, and then I'll flip the shaft over and weld 2 or 3 passes on the other side and keep working my way back and forth till I get it welded up completely. And I'll keep checking it. Once I get the welds on this side, I'll spin it and check it, see how true it runs. I can kind of bump it around with a hammer to get it to run fairly true, close enough. And then normally once you get a few passes on each side and you keep working back and forth, it stays pretty much where it's at. But the first thing we need to do is preheat this to 900 degrees or so. And I've got temperature sticks, but I'm probably just going to do it by eye. The nice thing about steel, if you're heating steel, you can tell by the color the steel turns how hot it is within reason. Steel is normally silver, and as you heat it up, you get up to around 400 degrees, it starts turning what they call a straw color. You can kind of see it here. It's kind of a real light brown color. And then as it heats up more, that straw gets darker and darker until it starts turning really dark, and then it starts turning blue. And when it gets to blue, that's around 600 degrees. And then the more you heat it, it'll get a darker blue, and eventually it'll turn purpley looking. That's around 900 degrees. And you start getting up around 1,000 or so, you start getting a little bit of red color in the shaft, and then it gets a little harder to tell how hot it is because it's just glowing red. I mean, you can kind of tell basically because it'll be a dull red, and then when it gets a really bright red, you know it's really hot. So, but normally for welding purposes, what we're doing, usually around 900 degrees to 1,000 degrees is plenty hot enough for any shaft you're going to weld. The key to it is you want to try to maintain that 900 degrees the whole time you're welding on it, and sometimes on really big shafts, this shaft's small enough I don't think it'll be a problem. On really big shafts, sometimes you have to stop and put the torch on it and heat it up again and then continue welding. You might have to do that 3 or 4 times till you get it completely welded up. And then when you get done welding, you want to post heat it with the torch back up to 900 degrees or so, and then you wrap it up. And the old days, back when I was 17 years old, we actually used asbestos sheeting to wrap around a shaft like this to keep it from cooling down too fast, until we discovered asbestos can cause lung cancer, and we quit doing that. And we actually started using fiberglass insulation, which to me is no better. I think the fumes coming off that are probably as bad or worse for you than asbestos is. So we ended up coming up with some fireproof blankets and stuff to wrap things in. Anytime you stub a shaft or you're doing something that the strength is critical on it, again, you want to look at preheating, post-heating, and using the correct rod. Now, when you're doing something that needs to be strong like this, you want to use a low hydrogen rod. There's 2 different low hydrogen rods I use mainly, and that is 70-18 rod and 110-18 rod. And the difference is 70-18 rod is basically the first 2 numbers on it is the tensile strength of it, so it's about 70,000 pounds tensile strength. And depending on what steel you're welding to, that a lot of times that's not quite as strong as the steel you're welding to. So then you have to move up to this, which is 110-18 welding rod. Again, it's a low hydrogen rod. You have to run it on DC reverse, and that's one of the disadvantages of the low hydrogen rod. Most people, they buy an AC welder, and if they're using 6011, 6013, something like that, you can run it on it no problem. But when you want to go into the higher alloy rods and low hydrogens and things, you can't run them on there because they won't run properly. So you want to make sure whatever rod you're getting, your machine will run them. You have to get a machine that's AC DC so you can switch it to DC, and you got DC positive or DC reverse, and so you'll make sure you have it set correctly too. You run this on DC reverse. So anyway, let me get the torch set up. We'll go ahead and get this heated up to 900 degrees, and we'll start welding on it. Okay, I have it all wrapped up here in a fiberglass blanket, let it cool out real slow. I probably won't mess with it now till, I don't know if I'll get around to it tomorrow or not. Tomorrow's Saturday, June the 7th, so we'll see. I used 5 rods total. I'll show you my welder over here. I've got a Miller, it's a Dial-Arc 250. It's AC DC. So if you're running AC, you plug in over here on the right. If you're running DC, you plug in here. Okay, it looks like we got this all ready and machined, and all it needs now is a keyway. This is the old keyway. You can see it's didn't clean up all the way. That's not going to hurt anything. So I'm going to have a keyway cut on this other side here. Unfortunately, this is goes on the machine that I need in order to be able to cut a keyway. So I'm going to have to take it to a local shop here and have them cut the keyway in there for me. I've got the end drilled and tapped. It's cut the length. Everything's the diameter. Once we get the keyway cut in there, we can start putting the motor back together and then start mounting it back on the mill. So today is Sunday, so I'm going to call the machine shop tomorrow and see how quick they can get this in and get it cut for me. It shouldn't take too long. The only problem is this is a metric key. A standard key, which is in this shaft now, is a 1/4 inch wide key. This one is like 234 thousandths. So if he doesn't have a metric end mill, it's no big deal. You just take a 3/16 end mill and cut down and then move over and cut each side to get it out to the right width. Takes a little bit longer, but it's very doable. You don't have to have any special tooling or anything. So anyway, that's where we're at right now on this thing. So I'm gonna call it a day and catch up with you later. Okay, so I got my motor back from the machine shop today. I just went and picked it up. Had to have the keyway cut in it. I could machine everything, but I had no way to cut the keyway in it easily. I could use that smithy I have, but it wouldn't do a real good job. It'd be a real pain setting it up. So there's a local machine shop I went to, and he did a really good job cutting me a new keyway in there. So now it's just a matter of putting this back together. like new. Okay, so it's all back together now. What I'm going to do is I'm going to wipe it down with some acetone. I'm going to mask off my labels and I'm going to paint it. Okay, there's one thing I want to check. I want to check on my old motor from this face to the end of the shaft and compare it to the other one. Make sure I got my dimensions right. Okay, that's just a 4 5/8. 4 5/8. Okay, so we're ready to put the new motor on the mill. A couple of things. This is the original motor, and as you can see, there's 3 inches difference from here to here and from here to here. The new motor's 3 inches taller than the old motor, which isn't going to hurt things once I get it in there, but I'll show you here in just a second that it's going to be a little bit tricky getting it in there because of the height difference. And also, this old motor weighed 66 pounds. This motor weighs 95, so trying to pick it up and get it up underneath that head and everything, it's going to be a chore. So let me show you what I got to do. I've only got like 14.5 inches from here to here, which I need 17 inches to get the shaft underneath here. So I can come in and kind of tip the motor, slide it down onto this board, and have the shaft go up into here. Or what I can do is I can tilt this head a little bit, slide the motor under it, and then tilt it back, and I think that's what I'm going to do. So the way to tilt this head is you got this screw here, and you have to loosen up these 4 bolts, and then you can tilt the head. So what I'm going to do is I'm going to tilt it up a little ways, not real far, just enough where I can kind of get that motor underneath it. You can kind of see there. I'm going to try to come in here from this side, slide the motor up into here. So let me get it set up and we'll do that. What I have to do first is I got to put the other half of that pulley in. I'm going to have to put this up inside of here because it won't go in from the top. It's got to come in from the bottom, and it's got to go in first before the motor can go in. Then I have to put this half on the motor. It goes on like that. Okay, let's try this again. I'll take that board out of there and just lay a rag here for it. That'll give me a little bit more room. Boy, being 30 pounds heavier definitely doesn't make it easy. Okay, so I'm going to go ahead and crank this back down flat. And now I can crank the whole table up and raise that up into position. That's the plan anyway. We'll see how that works out. There we go. Okay. That should be down where it belongs. Okay, let's go up a little bit more. Okay, I'm having a problem here. This is hitting. I may have to take this box off. Now I need to rotate this around and my ears line up over here. Now I have to put this spring in here, and somehow I got to compress that down because this has to go down all the way on there like that, and then that has to compress down into that hole, and there's a shoulder on the bushing. You see it right here, and it goes down into that hole and compresses the spring, and that what puts the pressure on the belt. Okay, I'm going to try this first. I'm going to compress this down and try to pull it down with the zip ties and see if it'll hold it. The spring's not really that heavy of a spring. Okay, so I put about 1,000,000 zip ties around that spring and got it pulled down in there. I think I can get the bolt in it now, but I'm not sure if this is going to work where I can get the zip ties back out. We'll see. Okay, I'm going to go get my nippers and start nipping these off and see if I can pull them out. I've got this started down on there. It should be enough to hold it in there, I hope. Okay, so that worked pretty good putting the zip ties on there, and they actually came out easier than I thought they would. I just have to finish tightening this down now. One thing I noticed, I wonder what these holes here were for. I really wasn't paying attention, but if you look down in the piece down between the spring there, you can see a threaded hole. So what you do is you put probably, I'm sure those are metric, because this hole's metric. But what you do is you would put like a long piece of all thread in there, screw it down, and then you could pull this down because there's one on each side. You could pull it down, tighten it, and put this bolt in. But I didn't see that till after I had it this as far as I got it. So this is going to work, but next time I need to look at that and probably get some metric all thread or some really long metric bolts that would fit in that, and then I could just tighten it down. But live and learn. Okay, so I'm going to go ahead and finish tightening this down, and then we'll put this cover on. Okay, so I think we're ready to rotate this around and put the box back on the back and hook the wire back up. And we should be ready to go. I'm kind of holding up on this motor as I'm cranking it up because that little worm gear, the shaft's not very big in it, and I have seen those break before if you're trying to pick all this weight up, the leverage of that. So you want to be aware of that when you have it tipped over this far. If you're going like 45 or something like that, it's no big deal, but if you go all the way around like this, you want to be careful because if you just crank it up, you could snap that shaft off and this thing will fall down, and then you can't move it anymore without fixing that. Okay. Let's see, I need, I'm going to crank this around a little bit more because my thing's on the bottom there. Okay, I'm going to have to move the camera out of the way again. Okay, really dummy me, I wasn't paying attention. I heard something pop when I was cranking it. I didn't notice it pulled this wire out of here. I should have flipped that around the other side of the head before I did this. So now, rather than crank it all the way down, I'm just going to unwire it in here, right up the other side and wire it back in. So, making work for myself, what can I say? Okay, so we're ready to start wiring on going 240 volt with 3-phase. You have to hook 4, 5, and 6 together. And then for line 1, you have wire number 1 and 7 coming out of the motor is hooked to line 1. On line 2, you have wire 2 and 8 hooked together going to line 2. And then you have 3 and 9 hooked together going to line 3. So I'm going to go ahead and hook that up now here, and then we'll fire it up and see if I got it going the right direction. If it's going the wrong direction for what I want it to do, you just switch any 2 of these wires, any 2 of the main leads coming in, and it'll reverse the rotation. So I'll show you that. Okay, we're ready to try this. I'm going to put it in low speed because I've got this cranked out all the way as fast as it'll go, because I had to do that so it'd give me as much play as possible on the motor pulley to get that put back together. So I don't want it screaming in open belt, so I'll have it in back gear, so it should go slower. It's still going to go really fast, but I can crank it down as soon as it fires up. So I'm going to start the phase converter here. Turn the breaker on that. Okay, let's try open belt. Wow. That sounds nice and quiet. And it's actually going the right direction. When I turn it this way in open belt, I want it to turn this direction, and that's what it's doing, so I don't need to switch my wires around. I got it right the first time. It's kind of 50-50 because on 3-phase, if you switch any 2 of the wires, it'll reverse the rotation. So fortunately, it's going the right direction. I don't need to change any of my wires, so I'll go ahead and put the cover on it. And then I'm going to show you how to tram this head in, because when you crank it, you lose your orientation with the table. So when I crank it back up again, I got to dial in on the table to make sure it's perfectly square with the table. So we'll do that after I get the cover put on the wires. Okay, I'm going to set up my dial indicator here to tram this table in. And I mean, they make tools you can buy. It's got 2 indicators on it and all that stuff. This works just fine. And I normally just try to make a radius or a swooping circle the width of my table. That gets me out. My table's 9 inches, so basically I'll be doing a circle 9 inches or a little less than that to stay on the table. And that's usually close enough. So what I want to do first is I'm going to change the end on my indicator. I already screwed the old one off. And then I've got this set here. It's got different tips in it. I like to use these big radius ones, so as I go across these T-slots, if you had just a regular tip, it'll drop down there and catch, and it'll knock your indicator out of square. So with this, you can run across the T-slots and not have it bump it out of square. And these just screw on like that, and just hand tighten it. You don't want it real tight. Okay, and then I want to move this in to where I'm straight up and down. Okay, I'm more concerned right now side to side because that's where I tipped it, but it could be on front to back, and you have to loosen different screws to make it go up and down front to back. Right now I'm just working side to side. I'll get that set first and I'll worry about front to back, but I can check them all at the same time. So what I'm going to do is come around just till I touch. Okay, so that's about 10 thousandths I've got on there. That's +1. Zero. So front to back, it's pretty good. -1. I can't believe I got it that close just by eye. So basically, I've just got to move it 1/1000th of an inch. So I might be able to bump it that much. Ooh, yeah. So that's 0, -1, -3/4 of a thousandth, minus about a half. So let me I'm going to snug these down now. Zero, -1. It's just about 3/10 of a thousandth, and that's a half. So front to back, I'm within a half. Side to side, I'm within about 3/10 of a thousandth. So that's pretty good for most of the stuff I do. I'm going to call that good enough for now. But that's how you can tram your table in. And that way you know your spindle's perfectly true with the table. So I bought a magnetic switch, and I'm going to mount it here somewhere on this box. I haven't decided yet. I was thinking maybe on the side here like that. And I'm going to run the 220 volt in through this magnetic switch. So you'll have to push that switch and that switch to run either the mill or the lathe. The good thing is when the power goes out and the power comes back on, the magnetic switches will kick out and there'll be no power going to either machine, so it's not going to burn either machine up if I accidentally leave it on again like that. It's just going to be a safety thing. I'm not going to do that on this video. The next video I'll show wiring this up and show you how I did that. So anyway, I want to thank you guys for watching. Like I always say, have a great day and we'll see you on the next video.